Good morning to everyone. My name is V. Pansai Srinivas. I am from CSIT B section. My roll number is C7. Today's my topic is about high level computer architecture in COA. Introduction to high level computer architecture. High level computer architecture refers to the design and organization of a computer system at software and hardware level. It focuses on the abstract representation of a system, including the instruction set, architecture, and memory hierarchy. The goal of the high level computer architecture is to optimize performance, energy efficiency, and scalability while providing a user friendly interface. The simplified view of a computer personal computer architecture layer. Wet layer. Wet wave has user software have application programs, operating system utilizers, device drivers, and hardware contains hardware systems like CPU, printers, displays, and another the hardware examples. Instruction set architecture (ISA). ISA defines the interface between the hardware and software, including the instruction registers, memory organization, and addressing modes. It provides a set of instructions that a processor can execute, allowing the software developer to write program for a specific architecture. Different ISAs such as Z86, ARM, and MIPS have their own unique features, advantages, and trade-offs. Software has applications of operating system, compiler, utilizers, whereas interlinked with the IAS. And hardware contains as CPU, memory, I/O interface, I/O devices. Pipeline. Pipelining is a technique that allows multiple instructions to be executed simultaneously, overlapping their execution stages. It breaks down the execution of instructions into smaller stages, such as instruction fetch, decode, execute memory, access, and write back. Pipelining improves the performance by increasing the instruction throughput, but it introduces additional complexity due to dependencies hazards. For example, clock cycle, waiting instructions up to 0 to 8. Pipelining, stage 1 fetch, decode, execute, and write back. It is the pipelining technique. Caches. Caches are small, fast memory units that store frequently accessed data and instructions closer to the processor. They exploit the principle of locality, including temporal locality, reusing recently accessed data, and the spatial locality, accessing nearby data. Caches help reduce memory latency and bandwidth requirement, improving overall system performance. Memory hierarchy. The memory hierarchy consists of different levels of memory, including registers, cache, main memory, and secondary storage like hard disk drives. Each level offers different capacities, access speeds, and costs, with the higher level being faster but more efficiently. The memory hierarchy aims to bridge the gap between the fast but small registers and the higher but slower second storage. Computer memory hierarchy. At the bottom, versatile, very long term use. At the bottom, second, non volatile long term use. And bottom, third, non volatile short to long term use. And at the bottom, fourth, volatile very short term use, and top second volatile immediate term use, and first of the hierarchy is volatile near instantaneous use. Superscalar processors. Superscalar processors are capable of executing multiple instructions in parallel, exploiting instructions like parallelism (ILP). They feature multiple functional units and pipelines to enable simultaneous execution of independent instructions. Superscalar processors require a sophisticated hardware mechanisms to detect and resolve dependencies, ensuring correct execution. At the instruction fetching unit, it passes the data to the instruction queue. It passes to the dispatch unit, and dispatch unit are divided into floating point unit and integer unit, and these are connected to writing unit. This is the process with two execution units. Vector processors. Vector processors are specialized in execution operations on large area arrays of data using vector instructions. They exploit data level parallelism (DLP) by performing the same operation on multiple data elements simultaneously. Vector processors are commonly used in scientific and multimedia applications that involve heavy data processing. Vector processors, the supercomputers, optimized for vector and matrix operations. Main memory. Multi-core processors. Multi-core processors integrate multiple independent processing cores on a single chip. Each core can execute instructions independently, enabling parallel processing and improve overall performance. Multi-core processors require efficient task scheduling and synchronizing mechanism to fulfill utilize their parallelism. SIMD versus MIMD architectures. SIMD, single instruction multiple data architecture, executes the same instruction on multi-data simultaneously. MIMD, multiple instruction multiple data architectures are execute different instructions on different sets of data concurrently. SIMD architectures are sustainable for data parallel applications, while MIMD architectures are more flexible but require more complex hardware and software support. Instruction pool, power unit to the data pool. Virtual memory. Virtual memory is a memory management technique that allows the execution of a program larger than the physical memory capacity. It provides the execution of a larger address space by using secondary stage as an execution of the main memory. Virtual memory enables memory isolation, protection, and efficient memory allocation, and enhancing overall system reliability and flexibility. Cache coherence. Cache coherence refers to the consistency of a data stored in different caches that share the same memory allocation. It ensures that the all processor observed a single consisting view of a memory, even in the presence of the multi copies of a data. Cache coherence protocols such as MESI, modified executive shared invalid, manage the sharing and invalidation of a cache lines. Memory consistency models. Memory consistency models define the order in which the memory operations appear. Order in which the memory operation appear to be executed in a parallel system. They provide the rules and constraints for the ordering of a memory accesses, ensuring the correct behavior in a concurrent environment. Different memory consistence models such as sequential consistency and relaxed consistency, trade-off performance and programmer easy of use. Branch prediction. Branch prediction is a technique that attempts to guess the outcome of a branch instruction before it is actually executed. It happens mitigate at the performing impact of the conditional branches by speculatively executing the predicted part. Branch prediction algorithms such as static prediction and dynamic prediction aim to minimize the branch mispredictions. Instruction level parallelism ILP refers to the ability to execute multiple instructions in a parallel within a single program. It can be exploited through the technique like a pipelining, superscalar execution, and out of order execution. Maximizing ILP requires efficient hardware support, compiler optimization, and intelligent scheduling of instructions. Power and energy efficiency. Power and energy efficiency are critical factors in high level computer architecture. Techniques like voltage scaling, clock gating, and dynamic power management help reduce power consumption. Architectural optimization such as low power modes and energy aware scheduling aim to improve overall energy efficiency. RISC versus CISC architecture. RISC reduced instruction set to computer. Architectures have a simplified instruction set focusing on executing simple instructions quickly. CISC complex instruction set computers. Architectures support more complex instructions but tend to have more complicated microarchitectures. RISC architectures are known for their efficiency and scalability, while CISC architectures offer more instruction level functionality. Memory interleaving. Memory interleaving is a technique that distributes memory access across multiple memory modules or banks in parallel. It helps increase memory bandwidth and reduce contention, improving overall system performance. Memory interleaving requires careful addressing and memory mapping to ensure proper distribution of a data. Fault tolerance and reliability. High level computer architecture also consider fault tolerance and reliability accepts. Techniques like error correction codes and redundant components and fault detection mechanisms help to improve system reliability. Redundancy and fault tolerance are critical in mission critical systems where system failures can have severe constant consequences. Emerging trends in high level computer architecture. High level computer architecture is a rapidly evolving field deriving by emerging trends and technology advancements. Trends include the rise of heterogeneous architectures, machine learning, accelerators, neuromorphic computing, and quantum computing. These trends bring new challenges and opportunities for computer architects to design efficient and powerful systems. Conclusion. High level computer architecture plays a crucial role in designing efficient and scalable computer systems. It encompasses various aspects such as instruction set architecture, memory hierarchy, parallelism, and power optimization. Understanding high-level computer architecture helps to in developing better software and hardware solutions to meet the increasing demands of a modern computing. Thank you thank you for giving this opportunity.